Great. Thanks, Paige, for the introduction. And it's really great to be back here in Michigan. I actually gave a Midas seminar about 7 years ago. So Al Hero had invited me then, and he asked me to come back this time. So it's really great. I'm actually on sabbatical this academic year, and so I picked up too many affiliations at the moment. But spending time at the Kellogg School of Management, thinking about the intersection of public policy and business and AI in various ways. Right, so I'll jump right in, and I actually reworked my talk a little bit last night because I was inspired by sitting in this room. And I've kind of made it a little bit of an homage to Claude Shannon, who is arguably the most important alum of this university, the father of the digital age. And so, as you may know, he was born in 1916 in Gaylord, Michigan, and then grew up in Petoskey, so right at the northern tip of Michigan. Then came down here and graduated in 1936. And so a lot of the things that I'll be discussing are very much inspired by information theory. In one case, it's algorithms that are drawing on Shannon's lattice theory of information as a way to both do knowledge discovery and creativity. And then secondly, I'll be asking this question about what are the fundamental limits of creativity? Is there a fundamental tension between between novelty and utility or functionality in the domain? And can we characterize what those fundamental limits are? And I think that really gets to the heart of what creativity is in a sense. But then we can also ask algorithmic questions. Can we build AI systems that can achieve or at least approach those fundamental limits? Right, so let me jump right in. Shannon himself actually thought quite a bit about creative thinking. And in one of the only times he ever kind of self-reflected publicly, he put forth 6 principles for creative thinking. One is simplification, getting rid of enough detail for intuitive understanding. Second was similarity to a known problem, and here experience seemed to help. Third was to reformulate, to avoid getting in a rut. The fourth was generalization, which was the way he described it as more than the opposite of simplify. And I would encourage you to read the essay in full, where he gets into the subtleties of this point. Fifth was structural analysis, breaking problems into pieces. And sixth was inversion, working backwards from the desired result. I think these are kind of nice kind of tricks or principles for theoretical research. But I think one of the key questions we want to ask here is it possible to formalize? I think Shannon himself was actually the master of this. A lot of people describe him as the opposite of an applied mathematician. The way they describe it is that applied mathematicians work with models that other people develop and develop numerical methods and this and that. On the other hand, he was a model maker. He was the master of mathematization. Okay. Cool. And so what I want to spend some time on is creativity. And in particular, I'm going to focus on combinational or combinatorial creativity. And this is a form of creativity that's often discussed throughout the literature. In a variety of fields, whether in the psychology of creativity or otherwise. And one view of it was due to Kostler. So he had this notion of biassociation. And the basic thinking was that creativity doesn't appear from thin air, but it is actually a combining of existing things or ideas and shuffling them in new ways. Margaret Bowden, the cognitive scientist and computer scientist of creativity, she also describes combinational creativity as kind of the core to creativity. Even most of so-called H creativity she describes as combinational. Here H stands for historical, so things that are new for not just the creator, not for that individual, but for all of humanity, for all of history. The kind of the highest levels of creativity she describes largely as combinational by putting together unfamiliar combinations of familiar ideas. And so we're going to be focusing largely on this combinational or combinatorial style of creativity. Okay, and before I get into some more theorizing, I wanted to give a few examples. So one is some work we did in the last few years on concrete. Here it's concrete, the building material, not concrete, the abstract principle. And so, as you may know, 8% of worldwide carbon emissions are actually from cement production. And if you can reduce that, if you can have that, I mean, that would be the equivalent of removing all aviation, actually, right? So it's about 3% of global carbon emissions are from aviation. And so what we did was we took just a small amount of data, about 1,000 examples from the UCI repository, and ran them through a life cycle analysis, and then understood their various environmental impacts, as well as the different input variables. As you may know, concrete is made of cement, water, gravel, fly ash, slag, and a couple other things. And we trained a fairly small conditional variational autoencoder to be able to generate new concrete formulations. And we went ahead and did that. And so here in this figure, this is an isomap embedding, but all of these are training, and this is one of the generated formula. And what I'm showing in the pie chart markers is the fraction of cement in dark blue. Slag and fly ash are other cementitious materials that are industrial byproducts. And so you'll notice that, first of all, this is extrapolative. It's outside the scope of the training data. And moreover, it's using a lot less cement than what was in the training data. And so it's kind of a nice example of trying to be beyond what you've seen just in training. And we went ahead and actually made cylinders out of this and crushed them in the lab. And we were able to demonstrate that this was 50%, it's much stronger than traditional concrete. And moreover, the life cycle analysis has halved the carbon requirements, right? So a really compelling result. And then we worked with Meta. They were building a data center in northern Illinois. And so they actually poured our concrete in their data centers. So it's actually a lot of fun to go up to northern Illinois and walk on your own concrete. So just a really compelling result of a fairly simple algorithmic idea of generation, but huge impacts. What's happening now is actually there's a commitment from the Open Compute Project Foundation, OCP, which is a consortium of AI hyperscalers, including Meta, Google, Microsoft, NVIDIA, and others. And as they're building new data centers, they're going to be using our style of concrete, this AI-generated concrete. So potentially very large impacts in terms of sustainability. And moreover, Meta and our colleagues there have been building up a partnership with Holcim, which is the largest concrete and cement manufacturer in Australia, Azerbaijan, India, Switzerland, Latin America, and so on. And so they're going to be further optimizing and deploying our AI approach to concrete. So again, a very significant impact from a fairly simple algorithmic idea. And you'll notice that this kind of creativity involved remixing of cement and gravel and so on. We're continuing to push those same kinds of ideas in terms of AI generation in the wastewater treatment field as well. So Ensurus, as Paige mentioned, is a company I work with that focuses on AI for wastewater treatment. And so you'll notice that this kind of unit process diagram is very combinatorial as well. And so what one can do is try to optimize these treatment processes, and we can reduce energy requirements by about 30%, which is quite significant because in many municipalities, water treatment is the biggest user of energy. Okay, so those are some of the areas in engineering that we've been working in. Switching gears to culinary science, this is something I've been working on for a long time. I think Mario have you tried some of the dishes or no? Oh, so we should get you back at our house and cook this for you. But this is a Kenyan Brussels sprouts gratin, which was designed by the IBM Chef Watson system for culinary creativity. Something I worked on many years ago. And again, the interesting thing is how to take ingredients like butternut squash, dried cherries, almonds, and Brussels sprouts, and combine them into new culinary formulations. And so this was kind of pretty well received. It ended up having pretty big impacts as well. So this dessert here, the Caymanian plantain dessert that was in Wired magazine, was originally developed actually for my wife and I, our wedding reception. So this was the dessert we served our guests. So, a lot of personal stake in addition to the scholarly ones. And as I was mentioning, it had a pretty big impact where a lot of food companies have incorporated this technology into their internal R&D processes. So to take an example, McCormick's one skillet spice mixes that you can buy in grocery stores are developed using our Chef Watson technology. And James Rischione, the chef who was on the front page of the New York Times here. So we're working again together to see what we can do to improve kind of healthy eating. So we're building a new app called Cullen AI, where we're trying to see, can you personalize nutrition, but that's still flavorful. So that's kind of what we're up to. And another area we've been quite interested in, and this again kind of riffs a little bit on what Mario was saying yesterday, that if you can have kind of simulators of phenomena, then you can optimize in them. And so when I was at Salesforce, my colleagues developed this project called the AI Economist. And here the goal was to have a simplified simulation of a society and then have a special agent in this two-level reinforcement learning setting that was setting the rules of the platform, the taxation policy. And what the special agent was trying to do was maximize the product between productivity and equity. Whereas the regular agents were just trying to enhance their own productivity. And as you play the two-level game, what emerges is a tax policy. And it turned out that this dynamic tax policy that is the Stackelberg equilibrium is actually about 16% better than the best static tax policy that Emmanuel Saez from Harvard had derived. Right, so significant improvement in this metric by doing this kind of AI design of tax policy. And what we're doing these days is looking at a few other application areas using the same basic approach of resilient food supply chains, nuclear non-proliferation, and securing the information environment. So thinking about misinformation and information overload, and essentially developing taxation or information disclosure or other similar kinds of policies that might improve these kinds of large-scale societal systems. Cool. Another thing that I've been thinking a lot about is kind of creative policymaking. I was hoping to find a picture of Gerald Ford and Claude Shannon to put in here, but I went with me and President Biden. So I served in the White House last year, and a lot of executive policymaking in the Biden administration and previous ones was really concerned about trying to use existing authorities that Congress has given in novel and useful ways for the particular problem at hand. And this is kind of an interesting area. So we used to do this. I mean, this is what I did when I was at the National Security Council. You look through all the laws that are there, which authorities do you have, and which levers should I play in which ways, such that I can have a policy impact that I'm looking for. So, for example, in the AI executive order that the president signed in October of 2023, there were these various kind of existing authorities under Defense Production Acts and various other things. And so the basic question was, how can you be creative and put those together to have the impact you're looking for? And that's another like super interesting area of creativity is how to actually do this kind of creative policymaking in an AI supported way. Cool. So as you've seen, all the different examples I've used so far, whether it was culinary ingredients or gravel and cement or aspects of policy, like different existing acts and so on, they had existing parts, and what we were looking for is different ways to combine them, right? But a big question, I think, is in a lot of domains, which is like, where do the parts come from? Right? Like, how do you decompose things into parts, and then how do you recombine them? And so that's been kind of troubling for this idea of combinational or combinatorial creativity, right? Everyone see why? Like, if you don't have parts to decompose in, like how are you going to combinatorially, put them together? And so that's been something that's been driving a lot of our recent research. And so one area we've been working in specifically is music. So Shannon himself actually was a big music aficionado, so hopefully he would appreciate this. And he was also very interested in artificial intelligence. He was one of the organizers of the 1956 Dartmouth meeting and so on. And apparently he believed that the most promising new developments in information theory would come from work on very complex machines, especially from research into artificial intelligence. Okay. And so what we've done is we've developed a technique called information lattice learning, which is designed to do automatic knowledge discovery. So what we're trying to do is, say, learn the laws of music theory, to take the music example. Right, so we have, say, 370 chorales by Johann Sebastian Bach. That's how many he wrote. We want to feed it into some sort of algorithm to develop the laws of music theory. This has been done by hand for the last several hundred years. So Fuchs is a famous music theorist who was a contemporary of Bach, actually, and it was kind of interesting, their interplay. So Bach would compose new things and Fuchs would write new laws of music theory. But then when you have the laws of a given domain, then you can use those to be creative. And here there's components and so on. And this is very different than the prevailing paradigm of end-to-end training for things like large language models. So you wouldn't have this intermediary that's interpretable when you're training end-to-end. But here we explicitly want this, in part for human control and human understandability, but also it seems like the knowledge itself is actually quite valuable. So if you're a scientist, you might actually care about what's underlying the phenomena, et cetera. Okay. And what we want to learn is not just interpretable rules, which I'm hoping for, but we also want to learn interpretable hierarchies of interpretable rules. Right? So when you're learning music, you typically start with things like note names and so on. You learn chords, but then when you're learning, say, chord progressions, you don't learn that in terms of raw notes anymore. You learn it in terms of these intermediate things you've already learned. Right? It's this hierarchical way of doing knowledge discovery. And so that's what we're after as well. Okay? And so this idea of information lattice learning is the following. It's a little bit like Fourier analysis. So if you have a signal like this, in a Hilbert space, what you can do is decompose this using inner products with a basis, and you get these coefficients. But the downside with this is that the coefficients are, at least for me, like I don't find frequency components like super interpretable. I mean, I kind of know for music and sound what they are, but for other domains, like especially like images, like I find Fourier analysis very hard to understand as a human. On the other hand, for us, when we do information lattices, we want each node to have a very specific mechanistic explanation. And in our case, we'll typically have this be a group invariance. So each node in the decomposition corresponds to a particular symmetry that's present in the signal. And moreover, we want it to be self-exploratory, in the sense that we don't want much or any domain knowledge to be put in the first place. So we don't have very strong we have universal priors that encode very little domain knowledge. And the way we do that, again, is by drawing on group theoretic foundations. So symmetries are the core of it. And this ends up being a generalization of Claude Shannon's information lattice. And then secondly, we want it to be self-explanatory. So the entire learning process should be human interpretable, not just the final result. And the way we do that is we have an iterative student-teacher architecture for learning, which operates on this lattice structure, and that produces this interpretable hierarchy of interpretable concepts, as well as its trace. Okay? And the way this ends up working algorithmically is that there's two phases. One is this kind of constructing the abstraction universe. So this is drawing on very little amounts of domain knowledge. For example, that rotation and translation might be important, or addition and modulo sums might be interesting, or something like that. You could draw on core knowledge in cognitive science as an example. And this is ends up being a fairly difficult computational group theory problem, but you can solve it, and it's by tough, I mean tough by normal standards, but compared to training large LLMs, it's actually quite easy. So orders of magnitude less computation than training a big old LLM. Okay. And then the second phase is actually where you use data. So here I have not used any data. I'm constructing this abstraction universe, the structure of this lattice, and explicitly constructing it. And then the second is I take a little bit of data and I learn the laws from that. And as I was mentioning, these things can be universal fairly. So the same structure we've used in chemistry and in music, right? So the same structure of information lattice allows us to learn the laws of ionic compound formation as well as music theory. Okay, so just to give you a feel for this, right? So can someone tell me what concepts you might be able to induce from this collection of shapes? Does anyone see any categories that determine something? Color? Does anyone see color, red and blue? Yes? Okay. All right, so maybe you're seeing color. So that one way to induce a concept of color is by classifying the reds versus the blues. You might also be seeing things like number of sides or convexity. Right, so these are the kinds of concepts that you can induce by doing clustering, and they correspond essentially, and this is constructed to be easy to show on slides, but these are basically group theoretic invariances, right? And so you have different partitionings of the space based on these concepts, and that partitioning is where the concepts come from. So the more general view of this is that we want to take a data space X, like the space of shapes, and do a partitioning, and that is the abstraction. So if the space is, say, X1, X2, X3, X4, X5, X6, then we might say that the abstraction is that X1 and X6 go together, X3 goes on its own, and then X2, X4, X5 go together, right? And so a concept is one of these partition cells, like red and blue, and this can be encoded using a matrix. And then probabilistic rule is a pair, so it's an abstraction, this partition, together with the induced probability distribution. So once I group X1 and X6 together, I have some probability. X3 has some probability, and then X2, X4, X5 have some probability. And so these probabilistic rules, these are exactly what we're aiming to learn as we do our information lattice learning. Okay? And because of the nature of partitions, set partitions, there's an automatic lattice structure that follows. So you can take two partitions and refine them, take their join, take their meet, and then you get this other notion, red trigons, red tetragons, blue tetragons, and so on. And in particular, it's exactly this so-called partition lattice. That follows very naturally just from the fact that we're thinking about concepts as partitions, right? So we haven't asserted this. It kind of fell naturally from the fact we're thinking of abstraction as a form of partitioning. Okay, and there's actually a Bell number of these. It's a super exponential number of nodes that can happen, and to say nothing of the edges, but you can go ahead and do certain things with it. And once we did that, we realized that this actually corresponds to Shannon's lattice theory of information. This is a fairly obscure work of his. This was presented at the 1950 London Symposium on Information Theory, and then published as like a 3-page paper. And if you look it up on Google Scholar, it has about 200 citations, but of those, about 180 meant to cite his 1948 paper, right? So there's some mistakes in the literature, but so only like about 20 papers actually build on this. And the basic idea that he was after was that suppose I say something in English versus in Morse code versus in German. If they're reasonable translations of one another, then they're saying the same thing. They're carrying the same information. And the way he mathematized that was that if you have several random variables, if they're inducing the same sigma algebra, they have the same set partitions, then they are informationally equivalent. And so that's how he came about the information lattice, and we kind of came up with roughly the same idea, except that he assumed the probability measure was already known. So he, used entropies and so on. For us, the learning is done after the fact, and so we learn the statistics from the data rather than assuming the probability measure in the first place. Okay, so it was kind of nice to see that kind of we rediscovered in a way Shannon's lattice theory. Okay, so we've done phase one. We've constructed the abstraction universe. What is possible to learn? Now we need to do the learning. And so it turns out we developed a fairly simple algorithm to do this, a teacher-student idea. And so the student will start with no rules at all, an empty rule set, and then pass this on to the teacher. I'm sorry, the student will try to maximize randomness under the current rule set and pass that on to the teacher. So you can think of this as randomly pressing on the piano keys, right? As random as possible. The teacher will listen to that probability distribution and compare it against the input corpus, like the 300 chorales by Bach, and try to find the most discriminative rule. So what rule will be the reduce the KL divergence between what the student did and the teacher's corpus? And we'll give that to the student. So this is the first rule that's added, and that'll push us as close as we can with a single rule to the teacher. The student will be now being as random as possible under the first rule set, under the first rule. And send that composition to the teacher. The teacher will listen to this, find the second most discriminative rule, pass that, add to the rule set. The student keeps iterating and so on. And so you keep adding rules according to how discriminative they are in terms of getting to the input corpus. And here I described it as if you were getting a list of rules, but in fact we structure it according to the lattice. So we avoid redundancy, so you don't get things that are very close to each other in the lattice and so on. Okay, but I'll leave that detail for the paper. Okay, so what do you end up with once you do this? So some of the simplest of rules you get in, say, music are histograms like this, right? These probabilistic rules that probability mass is concentrated on C, D, E, F, G, A, and B, and very little on the others, right? And this is that the soprano voice is built on a diatonic scale, if you know a little bit about music terminology. But on the other hand, more complicated rules would be not expressed in raw notes anymore, but in terms of previously learned knowledge. And so you have this kind of rule that emerges. And if you know a little bit music, you can say that this means that individual perfect octaves are favored as most consonant, right? And so you might wonder, how difficult is it to go from the histograms to the words? Is this a lot of skill, or can anyone do this? And so what we did was we took freshman music theory students and asked them to do this, go from the histograms to the words. So there were 25 questions on their homework. 3 students got a 50, 7 students got between 40 and 50, and so on. 5 students didn't do the assignment, which is always a challenge for us teachers. So, but the point is that a good number of students who are literally just in their first course in music theory were able to do this translation pretty straightforwardly. Okay, so in that sense, we think it is quite human interpretable. And you might wonder, how much music theory do you actually recover by doing this? It turns out you actually recover quite a bit. So there's 75 topics that are taught in the first 3 music theory classes at Illinois. And so the ILL algorithm, just operating on the 370 chorales by Bach, recovered 45 of those. 7 were not recoverable because the data encoding didn't support those. And then we missed these 23. And we know exactly why 18 of them were missed, because they captured certain long-range phenomena that we didn't look at for computational reasons. Okay, and you also discover new things, right? You rediscover existing knowledge, but you also discover new things, which our colleagues in music theory actually find quite interesting. I'm not so skilled in music theory, so I won't describe, for example, this first one on unresolved tritones. But for this audience, I think you'll appreciate this abstraction that emerges, the second difference of pitch, right? The acceleration of pitch. And so that has not previously been described in music theory, and yet it is quite important in Bach's chorales and in music in general. So kind of acceleration of pitch seems to be kind of a very interesting concept, and our music theorist colleagues agree that maybe they should be studying the acceleration of pitch. Okay, and so once you have things set up like this, you can now do creativity. So I wanted to show you briefly this example. So here I'm going to take a song. I'll decompose it into what we call muons. For the physicists, apologies. We're reusing the word from particle physics, but these are abstractions of music, abstract pieces of harmony, rhythm, and melody. So let me show you this. So here, I'm going to play the original song first, and then I'll decompose it. You guys can hear that? Okay. Okay, so that's the original song. Now I'm going to just take its melody, one of the melodies. Right, so this is this. So that's Hey Jude by the Beatles. Another of the melodies that's in there is this one. This is Bach's Cello Suite. There's harmony. And again, just to emphasize the point, these are abstractions. So you won't hear this track directly in the song, but this harmony is in there. And then there's rhythm. So this is, again, the drum track's not there, but the rhythmic properties are there. Right, so now I'm going to put it all back together into this mosaic. Right. Right, so that starts to answer this question, where do the parts come from to do combinatorial creativity? Right, and let me show you, like once I'm able to do these muons, I'm going to show you how to actually do something. So let me do something simple, like I'm going to take the melody from Happy Birthday, which hopefully everyone's familiar with. I'll take the harmony as well, but I'll take the rhythm from, say, Mozart's K545 Piano Sonata, just as a reminder. It's fine, I'm almost done. So. Okay. Okay, so that was Mozart's Piano Sonata K545. So I'm going to take its rhythm. So when I'm doing these muons, I'm going down the lattice, right? I'm doing the decomposition. Now I'm going to let me pick an instrument. Okay. So now I'm going to go back up the lattice, right? So I did the decomposition. I'm going to do the recomposition. So I'm just going to AI glue it a couple times, right? So this is an example. Right, and the way you want to think about when you're going up the lattice is that the muons impose constraints, and so you can stochastically sample within the constraints, so you can get other things, like this is another example. Okay, so hopefully what I've tried to demonstrate here with this music example is that we have ways of now constructing parts and combining rules in settings where there's not obvious parts and combining rules. Like with culinary, it's pretty obvious there's ingredients and so on. Here, what we've done is tried to generate things to allow that. Okay, and what just happened? Okay. Okay. Good. Right. So good. So we've been able to use this AI music technology pretty considerably. It turns out that this is also useful for learning laws in, say, neurodevelopment. So you can think of gene activation patterns as kind of like music over time, and you can learn kind of the gene pathways. You can also think about questions in, say, machine vision. So you can do, say, MNIST classification with very, very small amounts of data. Right, so literally 4 examples of each digit are enough to get over 90% accuracy. On the other hand, the full MNIST data set is actually, I think, 6,000 examples of each. Right, so in the very tiny data regime, you can do much better than neural networks and so on. You can do things like the Omniglot challenge at nearly human levels, again, much better than neural networks. So this is our approach. Humans have access to extra information. They have stroke information, as does this Bayesian programming language approach. So we don't provide stroke information, and yet we're able to achieve much better than neural networks. And for example, for this quick draw setting, we're able to outperform vision transformers and all kinds of other things quite considerably, and almost at the human level. Okay. So this information lattice approach seems to be pretty powerful, and we're excited to see where we can take this in scientific discovery. So we're working on something related to super Yang-Mills theory, trying to understand how to compute scattering amplitudes. This has recently been pursued using transformers, but that's pretty much a black box. So we're hoping to kind of open the black box. As Mario described yesterday, quantum experiments, their combinatorial structure might be something one can think about using information lattices to simplify. And if you have, say, inorganic crystals that DeepMind developed, that's nice, but it would be nice if you had a way to find the laws of inorganic crystal formation. So that's another example that we've been thinking quite a bit about, because there hasn't been much development in the theory of inorganic crystals in the last several decades. Cool. So that was kind of the first big part of the talk. And then what I wanted to talk about secondly was the other inspiration from Shannon, which is fundamental limits. Right? So one can argue that what every engineer wants is a good set of limit theorems, like Pierce argued. And you might wonder why. Why don't I just build stuff, right? Why do I need limits and understanding of what's possible and what's impossible? And so there's a bunch of reasons. So as I'm building creativity algorithms, AI for creativity, I want to know what resources and performance criteria are fundamental and which are not. I want to demarcate what's possible from what's impossible. I want to provide design insights into operating at that boundary, which is to say architectures for optimal designs. And I want to be able to benchmark things, ask how close to optimal am I, rather than only comparing to previous technologies and so on. Right, and so you might have seen these fundamental limits in a variety of settings. So information theory is perhaps the most famous. So the fundamental limits of communication in the presence of noise, but also thermodynamic limits on the efficiency of engines, or how fast you can fly in a forest without crashing into trees. Sertaj Karaman was my roommate in grad school when he developed this, and I like to take slight credit for this, because I was fairly messy, and so he had to walk around my stuff when he was in our living room. So hopefully it was inspirational. Okay, so as we formalize, we want to think of creativity as the generation of an artifact that's judged to be novel and also to be appropriate, useful, or valuable by a knowledgeable social group. And what we want to do is kind of formalize these different notions of what artifact, novelty, utility, and knowledge are. We have, I'm not going to dwell on the details of this, but we have different ways of formalizing this in terms of kind of what artifacts are and how they're composed of components. And then we have the known set. These are things that are already known in the creative domain. And then there's a novelty function like Bayesian surprise and a utility function. And so once we have these kind of formalizations, we also think about a creativity algorithm as a formal thing. So we think of it as, again, as stochastic sampling, P capital alpha of lowercase alpha. So this is how you're drawing from the conceptual space. And you can think of a typical creativity algorithm as maybe degenerate. It's a delta function. You're picking the best thing, or you're sampling from a distribution and so on. Okay. And so once you have this kind of formalization, which kind of mirrors Shannon's formalization of a communication system, the funny thing that happens is actually the fundamental tension between novelty on the one hand and quality on the other is actually the same as Shannon's capacity cost function for communication. So what we're doing here is we're maximizing the expected novelty with respect to the new artifact and the inspiration set under a constraint that the expected quality is at least capital Q over the choice of the creativity algorithm. And what one can show is that the expected Bayesian surprise is actually Shannon's mutual information. And so this novelty quality trade-off is in fact maximizing mutual information under a cost constraint. It is literally the same as Shannon's capacity cost function. And so there's this very weird and interesting relationship between creativity on the one hand and communication on the other. And they're mathematically very, very linked. This optimizing P alpha actually describes an optimal creativity algorithm, which is not super helpful because it's not exactly constructive, but it still gives us insight into how to create well. It also gives us more general insight, like these trade-offs between quality and novelty that they might have this convexity and various other properties. Cool. So this is really this question of like, what are the limits of creativity? So it might be something like this. So everything below this line, this curve is possible. Everything beyond this curve is impossible. Okay. But how do we test this empirically? Because we might not have access to the distributions, right, of the priors and the conditional posteriors and so on. And so this other thing we've been looking at recently is how to bridge between statistical theories of creativity, like I just described, using mutual informations and Bayesian surprise, and bridge it with empirical or constructive distance-based notions of creativity. This is a more common thing that's done in the science of science, that you say, I look in some embedding space, I look at the different ideas that are being joined together, and if they're distant, that's more novel than if the ideas were already close to each other. Right? So people often build these networks and then look at kind of distant combinations and so on. Right? So is there a way to bridge between statistical things and distant metric things? And this was kind of a difficult question for us, but luckily Al Hero from Michigan had done this paper in 2002 that we were able to draw on. So what Al and his colleagues showed was that if you look at ideas from computational geometry. So if you look at Euclidean space, you throw down some random points according to some distribution P. You throw them down IID. And you look at some combinatorial structure through those points, like the traveling salesman tour or the minimum spanning tree. Then the length of that traveling salesman tour actually converges to the Rényi entropy. And in high dimensions, it converges to the Shannon entropy. Right? So like there's this very nice, cool bridge between statistical things and metrical things, and we're working on exploiting that right now. Okay. And I wanted to close with a little bit of discussion about LLMs because it's what everyone's talking about. And I don't know whether this is true, but Anthropic's LLM is called Claude. I'm not sure if it's actually named after Claude Shannon. Does anyone know? Yeah. It is? Okay. So I was right in my intuition. So Shannon originated language modeling in his 1948 paper. These LLMs are getting to be very good at things. And so one might wonder, what are their limits for scientific creativity? And so Aurora and Goyle a couple of years ago introduced a theory for emergence of complex skills in language models. And what they were arguing is that there's different discrete skills that LLMs learn as part of their learning process from different text pieces. And so they constructed this kind of skill graph. And the compositionality of the skills is what leads to different capabilities. And this was very inspiring for someone like me who's been thinking about combinations of ingredients for a long time. And so what we did was we took their basic model and analyzed it much more finely. We extended it a little bit. We had a little bit of a hierarchical cognitive architecture aspect to these skills. But at its core, it's this bipartite graph. And what we showed by doing analysis of this model is, first of all, that the so-called chinchilla scaling, that data size and model size need to scale with each other, is actually optimal, not just empirically, but theoretically. Secondly, we showed that there's actually a size scaling phase transition. So there's been a lot of debate in the literature, like are these kind of phase transitions or emergence of capabilities real or not? Here we showed in our model of language models that in fact there is a very precise phase transition. And moreover, that after you go through the phase transition, there is a plateau of capabilities. And further, that there can be not just one emergence and plateau, but several. And so this, again, seems to capture a lot of empirical phenomena around LLMs from a unified perspective that started with a fairly simple abstraction of skills. Okay, so just to close, one might ask, cool, I have LLMs, what should I do with them? And Royce and some of his friends have been working on AI-generated scientific ideas. And so the basic idea here, again, thinking about novelty and utility, is let's start with a novel scientific idea and try to boost its utility through different prompting techniques for LLMs. And what one finds is that one seems to be able to do this. So this is an example from that utility boosting of scientific ideas. So this was the initial idea that was there. And then this is after several iterations of boosting. You seem to get more useful ideas than you would otherwise. It's more detailed. It has kind of better descriptions and so on. Right. So this is something we're actively working on right now to see how can we, in this novelty utility space, use LLMs for hypothesis generation. We start with some point and can we push the utility? Then we have other algorithms we're thinking about for pushing the novelty so that we can actually constructively get to that frontier. Right. So that's where I wanted to end, and I'll end with this other picture. So does anyone know who this is here? So this is Vannevar Bush, so the MIT professor and the architect of the post-war science system in the US. And this is with his differential analyzer, the analog computer. Anyone have a guess on who this guy might be? The one who just barely made the picture. Right here. Yeah, that's Claude Shannon. Yeah, he was Vannevar Bush's assistant back in grad school. And the interesting thing is that so Bush, his kind of philosophy of science was very optimistic. Like he believed in these endless frontiers, that science can be the end-all of human achievement and human well-being. On the other hand, Shannon was very much concerned with limits, that the frontier is limited. And it seems to me that as we're thinking about AI for science, it's good to have this philosophy of optimism, like we can drive things very well, like Bush tried to argue, but only when we're cognizant of the fundamental limits. And that really helps us with putting our energies in places where we think we can actually make an impact, rather than kind of just trying to do everything as fast as we can. So I'll stop there, and happy to take questions.
All right, I already see one hand up.
Well, I have a technical great talk,
Please.
And I have a technical question about the lattice learning stuff. But first, I have to follow up on your last comment, because it's pretty well established that creativity only arises within constraints. If things are too unconstrained, people just flail. If they're too constrained, then you're not creative, but there's some middle ground where constraints can aid creativity, and I think that's just exactly closely linked to your last point.
Yeah, I agree. I mean, yeah, I think psychologists have often shown that more constraints often make you more creative, so yeah, I agree.
Okay, so on the lattice learning stuff, what I could not tell, it seemed almost implied by your examples, was that you can identify different ways to partition things, and then you can bring them back together again. But that suggests a lattice of 3 levels, right? The root node, the basic partition, and then their combination. But I've seen in your papers where there's more than 3 levels. Is that true? And can you give an example where that would occur?
Yeah. In fact, like I was mentioning, partition lattices actually have a Bell number of nodes, which is a super exponential number. And moreover, when you cast them as directed acyclic graphs, they have many, many levels, right? And so, I didn't mean to imply that there were only 3. And in particular, when I'm talking about decomposition, I'm going down the lattice however far I want to get to the most detailed descriptions, the most detailed concepts. And then I'm going back up the lattice. It's not like the nodes correspond to the full thing, the abstraction and the reconstruction.
I expected that, but I don't understand how it can happen. That is, do you have to have sub-partitions?
Yeah. So that's the nice thing about the lattice structure, that as you go downwards, it's a refinement, and so there's a natural hierarchical structure. In fact, as I think I might have mentioned, the group there's an equivalent in the discrete case. There's an equivalence between partition lattices and subgroup lattices, and so as you're going down, you're actually getting finer and finer quotienting of the subgroups. And so that's the way you want to think about it. You're quotienting and quotienting and quotienting as you're going down and down and down. And then when you're going back up, you're recombining, and so on. Does that make sense?
Thanks, very cool. Okay. Thanks, very cool talk. I'm very impressed by your real-world application of concrete. I was not aware of that. Congratulations to that. I have a question on an earlier part, namely you talked about creative policy making, and I would have expected that that's exactly one point where we don't want to have creativity. I would like to have very sober and non-creative laws instead of very exciting creative restrictions.
Yeah. So the laws are what they are, and so in the U.S. system at least, maybe it's different in other places, but the legislature and the executive branch are meant to be separated, and so the legislature grants the executive some authorities, and so there is some finite list of authorities which might not be obvious. I mean, it takes some effort to figure out what the authorities are, but eventually there are these authorities, and then the question is like how you construct policies out of the authorities that you have. And so that's where this so-called creative policy making comes, not in determining the laws, but using the authorities. Okay.
So as far as we look at his 1948 paper, and he talks about in the 7th chapter of it, the entropy of the source, and he calls it relative entropy, and then he ends up calling it redundancy. In his world, the source was a mind, was creating a message, and the destination was another mind receiving it. But he defines this relative entropy as the ratio between the entropy of the source and that of the symbols used. And I think it's interesting to think about the fact that it's a relative constraint. Max entropy in whatever domain you're working with fits in both of those, but then meaning, I think, comes in, which he throws out as his responsibility in the first part of the paper. He says, I'm only involved in the messaging here. I'm an engineer. But he says that 50% of the message is determined by the symbols, and the other part is free. I think of that as sort of your creativity to work with, and that freedom is within those relative bounds and then bound by 50% in the English language, as you showed up there.
Yeah.
Each of these different domains are going to have different entropies and different relative entropies, right? Depending on the symbols and the source. But I don't think this has ever been looked very closely at in terms of creativity. He absolved himself of meaning, and everybody let him get away with it.
Yeah. So I mean, as you're saying, I think the third sentence of the 1948 paper is that semantics are irrelevant to the communication problem that he studies there. But there's been a lot of recent work, I mean, even back in the 50s, but especially recently on so-called semantic communication. And a paper that we did last summer actually shows that this kind of abstraction that happens in the information lattice is a form of semantic compression, lossy semantic compression, because abstraction, we feel, is semantic compression. And in particular, what we showed in the paper in the summer was that you can define an appropriate rate distortion function, the limits of lossy compression, in a semantic sense, and the information lattice approach actually achieves those limits. And so it's actually quite neat that information lattices seem not only good for knowledge discovery and creativity, but also for semantic compression, getting down from the raw uncertainty in the symbols to the core semantic uncertainty.
Hi, thank you so much for your talk. I apologize if you covered this and I just didn't quite catch it, but could you talk about what these fundamental limits you're talking about actually are?
Yeah, so in creativity, what I argued is that there's fundamental limits on the trade-off between novelty on one hand and utility or functionality on the other. So that's what I mean by fundamental limits. In communication, it's the amount of bits that you can send over a noisy channel with arbitrarily small error probability. In thermodynamics, it's the efficiency of an engine, et cetera. So those are the kinds of things. So, but when we say fundamental limits, no matter how clever you are, no matter how many resources you use, you can never exceed those limits. Right? So it's an impossibility result.
Oh, thank you for the very interesting talk. So my question is in regard to human creativity and computational creativity, whether the information encoding processes set the limits of creativity, meaning that the information encoding in itself sets a limit of creativity that is much less than the fundamental limits.
Yeah, that's a good question. I have no idea. That's a good question to think about. Like as humans, I think this question of representation seems to be very fundamental. So like having a new representation seems to enable new forms of creativity. And Bowden often describes that as transformational creativity. But if you were to believe that like essentially like kind of syntax and the semantics essentially carries all the meaning, then the representation shouldn't matter. And so I think it's a very good question. Like I'm saying, like how does the encoding or the representation as you're describing, does that make the creativity more accessible in some way, like algorithmically, or how to even think about it? So I mean, I think this is an excellent question to consider.
So do you think if you have a highly efficient encoder, that you would have a universal sort of learner that can learn from very small data?
Yeah, I mean, I think that's right intuitively, but I have no kind of theoretical arguments for why. But it feels true to me intuitively, but I don't know.
Any other questions? Okay, thank you so much.
Great, thanks everyone.